You ever need to think about literally anything else? Like you just want something to fill your brain and take the space so that you can focus on that rather than the thing. That's what this is. A physics distraction, a thing to think about. Why not? I want to talk about two-photon absorption. So, the story starts in 1920 at the University of Göttingen. Physicist Peter Debye is leaving, and he nominates physicist Max Born to take his place. And Max Born has kind of made his mark by being a guy who knows quantum mechanics. His most famous work is probably with Heisenberg to formulate the matrix representation of quantum mechanics that we all know and love. But his kind of method was looking at classical experiments, looking at experiments with well-known results, and trying to interpret those results in quantum mechanics, coming up with a theoretical explanation for why those things work that way on the quantum mechanical level. Born, a theorist, is nominated to head this department, and instead he convinces the government of Germany to split the department in two and have one for theory and one for experiment. And he wants his friend and colleague and collaborator, James Franck, to come and be the experimental guy. It ends up that the department gets split into three, but like that doesn't matter. It's fine. Franck and Born now get to work together. So, James Franck is a brilliant experimentalist. Up to this date, all of his work had been done like in the area of quantum mechanics, in atomic physics, in spectral analysis, all that good stuff. His most famous experiment, for which they won a Nobel Prize, is with Gustav Hertz in 1925, the Franck-Hertz experiment. So this is the Franck-Hertz experiment. They have a vacuum tube with a drop of mercury in it. They heat the tube, and then they shoot an electric current through this tube. And what they want to look at is fluorescence. So you're probably familiar with a diagram that looks like this. You know, you have an electron at some ground state, a photon hits it and gets absorbed. That electron goes to a higher energy level, and then it emits a photon and goes back down. That emitted light is called luminescence, and there are two types. The first is fluorescence, where, you know, it just emits a photon and you get to see it. The second type of luminescence is called phosphorescence, and it's more complicated. It's related to quantum mechanical spin. Actually, it's very interesting, but it's not the topic of today's video. But you can tell the difference because a phosphorescent object will receive radiation and then it will emit radiation for much longer than in the fluorescence case. This is a side note, but one of the ways you can tell you're reading AI-generated text of people trying to solve a physics problem is that they will use those words interchangeably. Like in a physics paper where Franck is talking about fluorescence, he would never describe it as luminescence, even though fluorescence is a type of luminescence. You know what I mean? Yeah, I'm sure the AI will take care of it. So the Franck-Hertz experiment is studying fluorescence in 1914. They have their vacuum tubey with their mercury vapor and they're shooting electrons through it. And they are describing what happens with mechanics, like the collision of the electron with the mercury atom. Slow-moving electrons they describe as having elastic collisions. They'll just bounce off the mercury atom. But fast-moving electrons they observe to have an inelastic collision, meaning the electron hits the mercury atom and there is an exchange of energy, which, look back to our little diagram, the electron will impart some of its kinetic energy to that mercury atom, which will cause an electron to go to a higher energy state, and then it will emit a photon. The emission of those photons, the fluorescence, the results, looks something like this. This is a recreation of the plot. So I like, on Wikipedia they have a much better example of this same experiment done in the modern day but with neon. So that looks like this. So what they observe are distinct emission lines, which implies that energy is quantized. You are only seeing photons being emitted at very specific wavelengths. If energy was not quantized, you would see a smooth emission, just a blob of light. But you see lines, which means energy is quantized, which means Franck and Hertz have confirmed an earlier result of Albert Einstein about the photoelectric effect. But also, what they don't know is that while they're publishing this paper in 1914, a year earlier, Niels Bohr in 1913 published his Bohr model of the atom, which explained how electrons move with quantized energy levels. So they have also, without realizing it, confirmed the work of Niels Bohr. So that's what fluorescence is. That's one photon absorption, right? We did it. Okay, so Max and Born worked together at Göttingen. They have this awesome collaboration in the 1920s. Who knew? Theorists and experimentalists working together? Oh my gosh, I'm just kidding. We know. Of course we know that. Something else about the University of Göttingen, which is important to this story, is that as a whole, the department was incredibly supportive of women's rights to education and also research. So earlier, Debye, when he worked there, he had invited Emmy Noether to work there and be a professor, and he invited her there to habilitate. I don't understand the translation of this word, but I think it's similar to like a postdoc process, but in Germany. He invited her there when she couldn't get a position anywhere else. Also, I think her name's pronounced Hertha Sponer was there. Great, all around great. So women are there, they're doing stuff. You have this huge collaboration between theorists and experimentalists. What a wonderful place for physics. Amazing, Göttingen, who knew? Great. So now we have Maria Goeppert-Mayer. Well, she was Maria Goeppert at the time. She becomes Maria Goeppert-Mayer. Okay. She grew up in Göttingen because her father was a professor of pediatrics, and she was like a brilliant student. She was a brilliant mathematician. She wanted to study math, but imagine being in university in the 1920s and seeing all this quantum mechanics stuff. She is just persuaded by the quantum mechanics to study physics. So in 1926, she begins her PhD under Max Born at the University of Göttingen. We have to leave Göttingen and go to England just for a second. In 1927, Paul Dirac publishes a series of papers about the absorption and emission of photons with the quantum mechanics understanding. And for the first time, he describes observations that were previously not understood with the classical interpretation. For example, the width of spectral emission lines was an open question until you understand quantum mechanics. What's interesting, besides all of his correct results from Dirac, was that he had a novel mathematical method for solving these problems. So he would treat the photons as harmonic oscillators, and then he would describe the atom as a kind of energy field that the photon harmonic oscillator with a unique phase and energy interacted with. And the math here isn't really important. I'm just giving you like the tiniest kindergarten explanation. So he had this description of photons. He had this unique Hamiltonian for atoms and how those harmonic oscillator photons interacted with the atoms. And he used those to solve the Schrödinger equation for that system using second order perturbation theory, which is where, so imagine you have a system that's a cow, and that's too complicated to solve. Perturbation theory is where you take something you understand, like a sphere, and you just shift it a little bit towards the cow, and you make a spherical cow. And you can solve this problem, but you can't solve this very complicated problem. So you do the spherical cow. That's perturbation theory, taking a problem you understand and perturbing a little towards one you don't understand to get a new solution. How was that? Perturbation theory. So that's what Dirac did. He had this very unique but very complicated new mathematical way to solve quantum mechanics problems. Back to Germany. So Frank, it's 1928. He's doing these experiments with collisions and trying to understand how different systems get you different emissions. And one of the things he does is shoot really fast electrons at the mercury atoms, and he finds that you give kinetic energy to the mercury, but also the difference in the kinetic energy given and the electron is emitted as a photon. So it's like two things can happen. You can exchange the energy in different ways, but the photon is always emitted at the same wavelength, because of the quantum mechanics. Also, he simultaneously shoots slow and fast electrons at the mercury, and he finds that they can kind of hit at the same time and produce an emission. So it's like an atom can undergo two collisions at the same time. And this is where Maria Goeppert-Mayer enters, right? She's at this great university. She's very supported. She's a brilliant mathematician. She's studying under Born, a guy who really appreciates quantum mechanics, and she reads Dirac's papers and she understands them because she's a brilliant mathematician, and she sees how important and valuable this method of second order perturbation theory is to understanding complex quantum mechanics situations. But also, she's looking at Frank's experiments and she's like, two things happening at the same time. I could mathematically explain that situation using the tool that Dirac has shown in his 1927 papers. And oh my gosh, because her advisor is Born, he's like, that's a brilliant idea. That's exactly what I do. I look at experiments and I take the theory and I try to get the quantum mechanics solution. So because of this unique position she was in, where she's got this math and she's seeing these experiments, she describes something that hasn't happened. She describes a possible two-photon absorption situation. I don't think she would have called it two-photon absorption. I tried to find her thesis in English and I only found it in German, and I can't read German, but the photon term was coined in 1926 by Linus Pauling, but I don't think it was widely used until the 30s. So she probably just called it two absorption or something. Yeah. Okay. So what is two photon absorption? You know, it's exactly what you think it is. You have your standard picture. A photon hits an electron and is absorbed, and the electron jumps up to another energy shell, right? Two photon absorption is when two photons, and they can be the same wavelength. They're often just like shown in the picture as the same wavelength, but they could also be two different wavelengths as long as they add up to that original wavelength. And the idea is that if they hit that electron at the same time, it's the same thing. It's as if, oh, that electron received the same amount of energy, it jumps up, and it emits a photon of the same wavelength that happened in the one photon situation. Two photon absorption. So something Dirac described in his papers were like these double process events where there's a single quantum event, but within that you can have like a virtual state before something else happens, and you need to be aware of that virtual state to mathematically accurately describe the picture. And that's one of the unique mathematical tools that Dirac develops, that Maria Goeppert-Mayer then uses, because she's like, okay, you have that one photon and it puts you in this virtual state that's not enough energy to get you to the excited electron. So as long as within, it's like 1/100th of a femtosecond, you get that another photon to come in, you're bumped up to the real state, and you get an emission just like you would in one photon absorption. Really interesting. I find the whole virtual state thing very non-informative and confusing, because that state doesn't exist. The two photon absorption is a single quantum event. One thing happens. We couldn't observe the medium state, but it is used to understand the situation. It's kind of a mathematical tool. There you go. Okay. So I love this story, like just the importance of like a broad knowledge of topics. Like she sees the math from Dirac and she's like, whoa, that's really important. And she recognizes that. And then she sees the experiments and she's like, oh, I could apply this here. It takes knowledge of both for her to produce this amazing result. And her thesis is just widely acclaimed. It's like short but specific and like a perfect argument for presenting her idea. But my favorite thing about this story is that she publishes this in 1930, and it's not until 1961, 1960, the laser is invented, okay? And you can have beams of coherent, very specific wavelength light, and you can use those in experiments. And so, of course, immediately people do. And 1 year later, after the laser is invented, every physics lab has a laser. Everyone's doing all the things. Kaiser and Garrett published this paper of an observation of a two-photon excitation event. We did it. Imagine what that would feel like. You publish your thesis and you're like, this is a thing that could happen. I think this is a thing that could happen. Here's the cross section. Here's the time scale, I guess. And then 30 years later, they observe it and they're like, yeah, good job, you did. Like, wow, what a feeling. Amazing. Oh my God. Maria Goeppert-Mayer. What? Of course, I have talked about Maria Goeppert-Mayer before. She's a very famous Nobel Prize winning physicist. I talked about her in my nuclear video because she's one of the main people that described the nuclear shell model of the nucleus. And that's what she won her Nobel Prize for. And again, if you go back and watch that video, you'll see that I said she saw this interesting data. She saw those magic numbers and she was like, this requires explanation. This requires a quantum mechanical explanation, just like Warren had taught her. And she did the thing again. Amazing. Amazing. That's the end of the story. Maria Goeppert-Mayer, she finished her thesis actually from Johns Hopkins because her husband was also a physicist and he worked there. There's a whole story about that too. They wouldn't hire her. Oh my God, it's fine. It's fine. But the University of Göttingen kind of lost status as an amazing physics institution in 1933 when the Nazis came to power. All the good physicists left because the Nazis are the bad guys. The Nazis are the bad guys. That's it. So that's two-photon absorption, a cute little physics idea that was proven 30 years later. How fun. I love to see it. So I thought it would be fun to end with talking about where this idea is used. Two-photon absorption, two-photon excitation, that kind of thing. And it's probably mostly used in nonlinear optics components and devices. I don't want to get into all that. There's a huge field. Like all of the government contractors, nonlinear optics equipment, that's what they're doing. That is this idea. But instead I want to talk about biology. So you will see this in papers as 2PEF, usually two-photon excitation microscopy. I love saying that word, microscopy. So first, one-photon microscopy. You have like a laser and you have a little slide with a sample in it. And inside that sample are chemicals called fluorophores. And you shine a light on those and they absorb the light and then they emit it. They produce fluorescence. And you can use that emitted light to get a picture of the object and study it. One-photon microscopy. Two-photon microscopy is exactly what it sounds like. Instead of making those fluorophores fluoresce with one photon, you do it with two photon. Yeah, same thing. But this has, it turns out, a bunch of advantages over one photon excitation microscopy. So look at this picture. On side A, you have one photon excitation microscopy. The laser is a blue light shining through the slide with a material. This is a higher frequency, so lower wavelength of light, which will excite the fluorophore. But since you are shining this specific wavelength that will excite that fluorophore, the odds of collisions are high. So you're kind of lighting up the whole path of the laser beam, which means if you're studying the object, using this technique, you're going to have a lot of background light. You're going to get a lot more light that's interfering with the actual sample that you want to look at. But look at the other side of the picture. This is two-photon excitation microscopy. You're shining a lower frequency but higher wavelength light. That's why it looks red instead of blue. So the odds of this happening, the odds of two photons hitting your fluorophore is lower. It means it only happens where the sample is. So you get a higher resolution and you are better able to study what you're looking at. Isn't that cool? Also, because you're using a lower energy beam, you can use this technique on living tissue and not like destroy your sample or your organism. Cool. I got this picture highlighting the difference and like the resolution of the image from this paper called When Two is Better Than One, which I think is funny. And you can see sometimes you're going to want to use two-photon excitation microscopy. Cool. But I wanted to end with a little thought, you know, something to think about, something to chew on over the rest of the day. If two-photon microscopy is better than one-photon microscopy, would three-photon microscopy be even better? I found this plot on Wikipedia which describes what I'm talking about. If instead of 2 hitting your little electron at the same time. Why not 3? Do you think that would be better? Would 26 photon excitation microscopy just be the most best image that you ever saw? Is there a limit to this technique? What is that limit? So I'm sure there's an answer to this question, but I didn't look it up. I thought it would be fun just to think about, like something to stick in your brain, and you can just, just spend the rest of the day trying to solve this problem. I realize this is going to make some people very angry that I'm not answering the question. I don't know the answer. I just thought we could think about it, together. Is there a limit to N photon excitation microscopy where like you're just not getting any more returns? So I know this will frustrate some people. I'm sorry. Let me tell you what I think. So one thing to notice, like from this picture, is that the emission goes down. So while in 2-photon excitation microscopy you are getting a better image, there's overall less light coming out. Overall, like emitted light is less, meaning the more photons you use for your excitation microscopy, the lower the emission rate, which means your image is going to get harder to see. So I imagine that is one of the limits on this idea. Like eventually the odds of 10 or 5 photons hitting your fluorophore at the same time are just going to be so small that statistically you will never get an emission, right? So that's one limit. But also there would be like a hardware limit. Like you would have to make a laser that can very realistically and specifically shoot a photon at like 1/26th or whatever of 460 nanometers. And how do you get a laser that accurate? Accurate enough to actually to do 26 PEM. You can't do that. So I bet, again, I don't know. I imagine that the limit is probably 3-photon excitation microscopy. And I bet 2-photon excitation microscopy is like the sweet spot where it's feasible but also useful, and maybe there are specific applications for doing the 3 photons. But I don't know. What do you think? Why don't you just think on that? Like, what a fun thing to spend the rest of the day thinking about. You don't have anything else going on, do you? Like, this could be a fun little thought experiment. Just turn off your TV and stop scrolling and just photons.